Have you ever wondered whether light is a wave or a particle? What if I told you it's both? This mind-bending concept is known as wave-particle duality, and it's one of the weirdest and most fundamental ideas in quantum physics. In this video, we'll explore the origins of this idea, the key experiments that shaped our understanding, and what it means for the nature of reality. Stick around until the end, because we'll also discuss how this bizarre quantum behavior is paving the way for revolutionary technologies like quantum computing. Let's dive in. The debate about the nature of light goes back centuries. In the 17th century, Isaac Newton proposed that light was made up of tiny particles, or corpuscles. This idea seemed to explain how light traveled in straight lines and reflected off surfaces. However, in 1801, Thomas Young conducted his famous double-slit experiment, which showed that light behaves like a wave, producing an interference pattern. This was strong evidence that light wasn't made of particles, but rather waves. So, case closed, right? Light is a wave. Well, not so fast. In 1905, Albert Einstein studied the photoelectric effect, where light shining on metal could eject electrons. The results could only be explained if light were made of particles, later called photons. This earned Einstein the Nobel Prize in 1921 and reopened the debate. If light is a wave, how could it knock electrons loose like tiny particles of energy? This led to the revolutionary idea that light, and even matter, can behave as both a wave and a particle. Wave-particle duality means that, depending on how we observe it, light, and even matter, can behave as a wave or a particle. But what does that actually mean? Think of ocean waves. They spread out, interfere, and create patterns. That's what light does in the double-slit experiment. But in other cases, like the photoelectric effect, light behaves as if it's made up of individual packets of energy, particles. And here's where things get even weirder. It's not just light that does this. Electrons, atoms, and even molecules exhibit the same dual nature. In 1924, physicist Louis de Broglie proposed that particles, like electrons, also have wave-like properties. He came up with the equation lambda equals hp, where lambda is wavelength, h is Planck's constant, and p is momentum. This means that the smaller the momentum of a particle, the larger its associated wavelength. This was later confirmed by experiments, changing our understanding of matter forever. One of the most famous experiments demonstrating wave-particle duality is the double-slit experiment. Here's how it works. If we fire a beam of light or electrons through two closely spaced slits, we see an interference pattern, the kind we'd expect from waves. But if we send particles through one by one and measure which slit each one goes through, the pattern disappears, and they behave like particles instead. It's as if the electron knows it's being observed and changes its behavior accordingly. This has puzzled scientists for decades. How does observation change reality? Another key experiment was the Davisson-Germer experiment in 1927. Scientists Clinton Davisson and Lester Germer fired electrons at a crystal surface and discovered that they diffracted like waves, creating an interference pattern. This was direct proof that electrons, thought to be particles, also have wave properties. It wasn't just light behaving in this strange way. All matter follows quantum mechanical rules. The discovery of wave-particle duality played a crucial role in the development of quantum mechanics. Physicists like Erwin Schrödinger and Werner Heisenberg built mathematical models to explain these behaviors. Schrödinger's equation describes how quantum wave functions evolve, and Heisenberg's uncertainty principle states that we can't simultaneously know a particle's exact position and momentum. These ideas form the foundation of modern quantum physics. Wave-particle duality also ties into another mind-blowing concept, quantum superposition. This means a particle can exist in multiple states at once until it's observed. This principle is used in quantum computing, where qubits can be both 0 and 1 at the same time, allowing for powerful parallel computations. You might be wondering, does wave-particle duality have any practical applications? Absolutely. Quantum mechanics, including wave-particle duality, is at the heart of many modern technologies. Lasers, semiconductors, electron microscopes, and even quantum computing all rely on quantum principles. In fact, Without quantum physics, we wouldn't have the microchips that power your phone or computer. Wave-particle duality challenges our classical intuition and plays a crucial role in quantum mechanics. It has revolutionized physics and continues to push the boundaries of technology. But there's still so much we don't fully understand, like what really happens when we observe a quantum system. Could this lead to new discoveries about the nature of reality itself? Only time will tell. Now it's your turn. What do you think about wave-particle duality? Do you find it exciting or just plain weird? Let us know in the comments. And if you enjoyed this video, be sure to like, share, and subscribe for more deep dives into the mysteries of the universe. Thanks for watching, and I'll see you in the next video.